Okay, good morning, everyone. Welcome to the NASA GIST Sea Level Rise Seminar. We're very glad to have Luke Trusel today. Dr. Trusel is an assistant professor of geography in the Department of Geography at Penn State University. He is an Earth system geographer whose research focuses on understanding the impacts of climate variability and change on the Antarctic and Greenland ice sheets. And specifically, his work focuses on assessing ice sheet surface mass balance and hydrological processes and seeking to advance understanding of high latitude environments as coupled ice ocean atmosphere systems. And he has demonstrated that he's demonstrated unprecedented acceleration of Greenland ice sheet melting in response to industrial era warming, as well as showing that atmospheric warming may threaten the viability of Antarctic ice shelves. And prior to joining Penn State Geography, Dr. Trusel served as an assistant professor in the School of Earth and Environment at Rowan University and as a postdoctoral scholar in geology and geophysics at Woods Hole Oceanographic Institution. And Dr. Trusel earned his PhD in geography from Clark University, where he was a NASA Earth and Space Science Fellow. So today he will be speaking on the topic Antarctica's surface mass balance in a changing cryosphere-climate system. So welcome, Luke.
Okay, can you see my screen? Good.
Yes.
Okay. All right. Okay, yeah, thanks so much, Patrick, for that introduction. And thanks for inviting me. Thanks for everyone for attending today. It's really great to be able to share some of our recent work with you all as it relates to Antarctica's surface mass balance and its coupling with and changes alongside the broader cryosphere climate system. And so this is work that I've advanced recently at Penn State with the support of the NASA Cryospheric Sciences program. Okay, and so we probably all know this, but to set the stage, right, the Antarctic and Greenland ice sheets contain immense amounts of ice, something like 99% of the Earth's fresh water, and therefore even modest changes in their total mass, which is somewhere around 29 million cubic kilometers or gigatons, that would have globally significant consequences in terms of contributions to global sea level and the associated impacts for coastlines and coastal populations worldwide. And so at the heart of studying ice sheets is trying to understand what and how they're contributing to sea level, both today and in the future. And so we really have quite wonderful observations showing that both of the ice sheets today are out of equilibrium with the current climate system. Both Greenland and Antarctica are losing more mass each year than they are gaining via snowfall. For Greenland, this is mainly driven by increased melting and runoff at the ice sheet surface. On the other hand, Antarctica, while it's also losing mass, most of that meltwater is thought to refreeze within the near surface snow and firn. And so the driving processes in Antarctica today are not top down like they are in Greenland, but essentially because the ocean is eating away at the ice sheet margins. And so where that ice sheet ocean interface is shown here in these gray areas, these are ice shelves where about 70% of the Antarctic ice sheet meets the ocean, and these play a critical role in holding back that 58 meters of sea level equivalent that I showed on that last slide. And so where we see the, excuse me, where we see the largest changes in mass today for Antarctica, these are where ice shelves have been disrupted, largely due to ocean melting, and as a consequence, the flow of ice has accelerated. And so we can quantify that mass change as somewhere in the ballpark of around 600 gigatons per year of mass loss from Antarctica, Greenland, and the world's glaciers and ice caps, although there are important interannual variations that I'll talk about today. But to put that number into a visual that many of us may be able to tangibly appreciate, at least those of us who have been to Niagara Falls as shown here, that 1 year of recent ice melt would be about equal to 9 years of Niagara Falls running continuously. And so this is an immense amount of water that's adding to sea level each year with really immense consequences for coastlines and people. So we really need to understand the processes of mass change at the ice sheets. And one thing we need to recognize is that the ice sheets are part of this coupled cryosphere-climate system. There's an interplay between the ice and the oceans and connections between the ice and the atmosphere and the ocean. And so the ice sheets gain mass at their surfaces. This is something we call the surface mass balance, or SMB. They gain this mass through snowfall. And if we think about where this precipitation came from that is landing on the ice sheets, this originated as evaporation off of the ocean surface. And so they're losing mass through melting and runoff, as well as the calving of icebergs and the flow of ice into the ocean, returning that water back into the ocean. And so there's this budget, a mass balance, and that budget is currently negative. In Antarctica, this is primarily due to the ocean eating away at ice shelves and the flow of ice accelerating in response to that. And this is especially prominent in places like West Antarctica. And so this is a recent mass balance assessment showing areas of mass change, and these that are represented by these circles and the larger diameter here. The redder the colors, this represents greater mass losses. And so there's really concentrated mass losses in West Antarctica in this Amundsen Sea sector. And there are, of course, also concerns here about potential triggering of instabilities in the ice sheet system, whereby retreat of the ice sheet may become self-sustained. And so today it's really, again, that ice discharge that is driving overall total mass losses for Antarctica. However, what I will argue today is that surface mass balance is really critically important when considering the total mass balance of the ice sheet and its contributions to sea level. And so, right, that ocean is the primary culprit today in terms of mass losses from Antarctica. But what happens at the surface of the ice sheet is critically important. In some years, it snows more and the surface mass balance value is larger. And in some years, it snows less and that surface mass balance is lower. And so why does that matter? These are effectively subtractions from sea level. The water that falls as snow over the ice sheet was evaporated from the ocean. And so this is a plot showing the surface mass balance up until 2021, as estimated from the ERA5 reanalysis as precipitation minus evaporation. And the surface mass balance, the average here is maybe around 2,100 gigatons per year. And the ice discharge is equal to somewhere in the ballpark of 2,200 gigatons per year. And so the variability in surface mass balance really plays a major role in how much and indeed whether the Antarctic ice sheet contributes to sea level or subtracts from sea level in any given year. And so underscoring this point are the events of the year before last, so 2022, where more snow accumulated across the Antarctic ice sheet than in any year over at least the last 4 decades. And so this plot is showing the SMB estimated from 2 reanalyses, the MERA2 reanalysis, as well as ERA5, as well as estimated by the RACMO 2.3 P2 regional climate model. And so in each of these, the 2022 surface mass balance, which is for these last points here, this was higher than at any point since at least 1979. And so in total, we're talking about positive surface mass balance anomalies of roughly 300 to 350 gigatons over the grounded ice sheet. This is about a 3 standard deviation anomaly above a 1991 to 2020 30-year climatology. And so this would be even larger if we considered, this is just looking and thinking about the grounded ice sheet, but this surface mass balance anomaly would be even larger if we consider the snow that fell over ice shelves as well. And so this had major implications for overall ice sheet mass balance, and this is showing the NASA JPL produced time series of Antarctic mass change from GRACE. And total ice sheet mass balance was also positive over the course of the year. In fact, this was the highest on record. And this was really driven by that highly anomalous surface mass balance, which led to overall mass gains of approximately 300 gigatons over the calendar year 2022. And so this represents a subtraction of Antarctica from sea level in 2022 of about 0.85 millimeters. And so clearly, right, what's happening at the surface is very important, and there's a need to understand the mechanisms influencing the variability and trends in Antarctic surface mass balance. And so if we think back to that ice sheet ocean atmosphere diagram I showed a few slides ago, and think about where that snow is coming from, again, it's coming from evaporation off of the ocean surface. So there's this fundamental connection between the ocean surface and the surface mass balance of Antarctica. And one mechanism that might influence this exchange of moisture, but also heat, between the ocean and the atmosphere is sea ice, as it really represents this physical barrier between the ocean and atmosphere, and its variability over space and time could effectively modulate that exchange between the ocean and the atmosphere. And so this brings us to thinking about what's going on today around Antarctica. And over the satellite era, Antarctic sea ice has been pretty steady, at least up until 2016, where it's really kind of fallen off a cliff. Unfortunately, though, most climate models that we use to make projections in the future of Antarctic climate and its surface mass balance really struggle with representing Antarctic sea ice. Most of these suggest a declining sea ice trend that are counter to our recent observations. And this is a figure produced by Letty Roach in 2020 in GRL. And so I think this raises a couple questions. What exactly is the effect of sea ice variability or its overall expansion, as well as its recent contraction on the surface mass balance of the Antarctic ice sheets? And if we use those same models that struggle to represent Antarctic sea ice today to project surface mass balance for the ice sheet, can we trust those projections of surface mass balance and therefore total Antarctic ice sheet mass change and contributions to sea level? I think these are important questions. They're motivating some of the research that I'm presenting here today. And so the short story here is that with observations, we see that in general, that when there's less sea ice offshore, there's more snow over the ice sheet. And so exploring the sort of physical connections between the ocean surface, the atmosphere, and the ice sheet surface are really major goals of a NASA-funded project that I've been leading. And this is showing strong anti-correlations between regional sea ice and ice sheet SMB. So if we kind of slice Antarctica, the ice sheet, and the ocean sectors into various slices of pie, this is looking at the correlations between what's going on over the ice sheet in terms of snowfall mainly, and what's going on in terms of sea ice variability offshore. And there's a lot going on here. So let's kind of dim these other plots out and focus just on two West Antarctic sectors. And so what we see, the blue areas over the ocean, and this is showing when surface mass balance is in this kind of slice of the Antarctic pie, when it's high in this region, the areas of blue show where there's significant reductions in offshore sea ice. And so, right, again, so when there's less sea ice here, it's snowing more over this area of Antarctica. And then when we look at the sort of brown areas over the ice sheet, these are areas when the surface mass balance is low, meaning that there's very low snow accumulation across the ice sheet. There is much greater, significantly more sea ice in this kind of offshore sector. And so we see these kind of anti-correlations. When there's more sea ice, there's less snowfall. When there's less sea ice, there's more snowfall. And that suggests there might be some causal relationship between regional sea ice coverage and surface mass balance of the adjacent Antarctic ice sheet. And so we can also look at the atmospheric and SMB conditions during these sort of end-member years over the observational period. There's been a lot of variability in Antarctic sea ice, so we have some years where it's very high. We also have some years when it's very low. And what we're looking at here in the next few plots is when we take the lowest 5 sea ice years observed in terms of overall Antarctic sea ice, and subtract from those the 5 years of highest Antarctic sea ice. This is what it looks like, at least in terms of the sea ice concentration anomaly. What I'm showing here is areas that are sort of outlined for these various seasons, summer, fall, winter, and spring. The outlined areas are where the anomalies exceed interannual variability. And so these sort of stand out about beyond the ups and downs that we see from year to year. We see that there's the greatest reductions in sea ice in summer, fall, and winter. There's less change in spring. However, in these lowest annual sea ice years, there are also areas of sea ice gain. So in this Bellingshausen and sort of eastern Amundsen Sea sector, these are areas where, despite overall Antarctic sea ice being low, in these years there's slightly higher sea ice, but this does change based on the season, and the changes are not uniformly significant. If we look at now what is going on with air temperature during those same end member years, so the lowest sea ice years minus the highest 5 sea ice years, we can see that there is a strong positive air temperature anomaly that coincides with low sea ice. And this is especially prominent in these non-summer seasons, especially here in austral fall, March, April, May. And so what I'm showing here in these plots is, you might be able to make it out, where there are dotted areas. These are areas where the sea ice decline stood out above interannual variability. And so that's shown here. And so you can sort of make out where these air temperature, these positive anomalies in air temperature, these are spatially coinciding with those areas of greatest sea ice reduction. And so the largest changes here are in austral fall, March, April, May, and you can see that there are very large positive air temperature anomalies in the regions of sea ice decline. And to sort of gain an understanding of what's going on and what's really driving that increase in air temperature during these low sea ice years, these plots take a look at summer and autumn. These are the 2 seasons with the largest sea ice change. And it's looking at the surface energy budget and the various components of that surface energy budget. So shortwave net radiation, long wave radiation, and the turbulent fluxes here of sensible and latent heat. The areas that are outlined or hatched, enclosed in sort of this like black contour, that's again where the anomaly here of this variable stands out above interannual variability. And then the dotted areas sort of behind that, these are areas where that season had a significantly reduced sea ice coverage over that area. And what we can see that in summer is that the reduction in sea ice causes an increase in net shortwave radiation. And so there's a lower albedo, lower sea ice surface that's absorbing more solar radiation. This is adding energy to the ocean in summer and warming it. And so this is adding energy to the ocean surface where we have less sea ice. In austral autumn, there is less, the sun is of course less important during that season. And the biggest changes we see really are these large negative sensible and latent heat flux, anomalies that represent a transfer of both heat and moisture out of the ocean. And so essentially what we're seeing here is similar to what's been recently observed in the Arctic, that summertime heat in a reduced ice ocean surface is then stored, and then that heat is released in non-summer seasons. And this helps explain why we're seeing like big positive air temperature anomalies in these areas where there was reduced sea ice. We can also take a look at what's going on with evaporation. And this is showing evaporation anomalies. And so anything in the sort of darker blues are areas where there are large increases in evaporation from the ocean surface. This is from the AER5 reanalysis. This is especially prominent in non-summer seasons. So again, in fall and winter, really, in the areas of reduced sea ice, right? Those are those dotted areas. These are the areas with the largest increases in evaporation. And so there's more moisture coming out of the ocean surface, as we sort of saw before in that last slide, in terms of the negative latent heat flux. And so what does this mean for the surface mass balance and precipitation over the Antarctic ice sheet? And so if we look at precipitation, we see a lot of green in these plots on the right? And so these represent areas where there is higher precipitation during those low sea ice years. However, with the exception of maybe some small areas in this kind of like Adelie land area of East Antarctica, most of the precipitation changes don't stand out above interannual variability. And so as we saw in the initial time series of surface mass balance that I plotted, right, there's lots of ups and downs. There's a lot of interannual variability in surface mass balance and therefore precipitation, which is the main driver of that surface mass balance variability. And so it's really hard to see a precipitation signal that stands out above that large degree of interannual variability. And I think the bigger issue probably is that we can't really examine causal relationships using these correlation and composite analyses. And so it remains pretty difficult to attribute precipitation change, especially to changing ocean surface conditions. One attempt to try to address that is through something called causal effect networks analysis, or CEN. This is, in short, a statistical approach to try to understand and quantify causal relationships between variables within a system. And this approach assesses the directional influence that variables exert on each other, as well as the associated time lags. And this is work that a PhD student working with me, Jessica Cromer, has recently published in Geophysical Research Letters. And so we've applied this to monthly MERA-2 reanalysis data, as well as NASA sea ice observations to explore the potential causal sea ice ocean atmosphere relationships in the Amundsen Sea sector of West Antarctica. And so the CN is revealing essentially what we are interpreting as a positive feedback loop between sea ice area and integrated water vapor over the Amundsen Sea sector ocean. And so what this is showing is that there's a negative relationship between sea ice and integrated water vapor over the ocean. So when sea ice is low, then integrated water vapor is higher. And that then 1 month later feeds back on sea ice areas. So when there's more integrated water vapor over the ocean, this analysis suggests that that then further reduces sea ice area, which would increase the water vapor in the atmosphere, which then might reduce sea ice a month later. This also shows us that integrated water vapor has a positive causal relationship with both downward long wave radiation from the atmosphere, as well as the fraction of low cloud area over the ocean. And so when there's more water vapor in the atmosphere, we're getting a flux of long wave energy from that increased water vapor that's related to a reduction in sea ice. And this also results in an increase in clouds over the ocean. And there's also a positive causal relationship, according to the CN analysis, between this low cloud area fraction and snowfall over the ice shelves. And so what this is kind of showing is this causal chain between a reduction in sea ice, an increase in water vapor, an increase in clouds as a result, and an increase in snowfall over the ice shelves. And so there's definitely more going on here, including the likely identification of longer range moisture transport through the meridional component of integrated vapor transport. So this is probably showing some sort of longer range transport of moisture that's leading to snowfall over ice shelves. I'd be happy to talk about what else we see in this analysis, or refer you again to this paper here. But in essence, the CEN is revealing that lower sea ice offshore West Antarctica causes an increase in atmospheric water vapor that results in greater clouds, and that subsequently lead to increased snowfall over ice shelves. And so we're starting to, through observations and this approach, work out some of the causal interactions here. Another way to approach this, the sort of cause and effect question, is through climate model sensitivity studies. And we did that using simulations of the Community Earth System Model 2, or CESM2, that were generated under the Polar Amplification Model Intercomparison Project, or PAMIP. And so what we have are two 100-member ensembles of CESM2. One of these ensembles is during this pre-industrial time period with more extensive Antarctic sea ice, so colder, greater sea ice, 100 members of CSM2 with that. And then there's also one ensemble here with from a 2°C warmer world and correspondingly reduced Antarctic sea ice. And so what we've done here is difference these. These are atmosphere-only simulations, which allow us to really identify and examine the direct consequences or response of the atmosphere to reductions in sea ice. In terms of the magnitude of those reductions, they are larger in most months. In these, comparing this pre-industrial to the warmer future simulation in CESM2, they're larger compared to the observations. Reductions exist uniformly across Antarctica, which is also counter to kind of comparing those end member years over the observational era, where we saw some, some declines and then maybe some increases elsewhere. So we're seeing uniform reductions, and they exist in all seasons. It's about a 20% reduction in fall, winter, and spring, and about a 35% reduction in sea ice in austral summer. And so in response to that sea ice reduction, right, so we're isolating how the atmosphere has responded to removing sea ice from the ocean surface. What we see is that there is a significant surface air temperature warming in all seasons. And so these, again, like the previous plots, the reductions in sea ice are the dots, and then the sort of significant change in the variable that we're looking at are these kind of like hatched and outlined areas. And what we can see is that most prominently in winter, over these areas of sea ice reduction, we see the largest magnitude positive anomalies in surface air temperature, right? The largest increases in air temperature occurring where that sea ice has been reduced. And the largest seasonal changes are here in fall and winter, a little bit less so in spring, and the most muted response in austral summer. And so this is kind of taking a similar approach to what we did with the observations and those end member years, kind of comparing the lowest to the highest CS years. Now we're just looking at the results of the CESM2 experiments during low and high sea ice. And what we can see here are similar things in terms of the surface energy budget and its components. And here we're looking at the 2 seasons with largest sea ice change in the model simulations, which were summer and winter, although the changes in austral fall were very similar to what we see here. And so in summer, again, the sort of response that we get if we reduce ice on the ocean surface, we get an increased uptake of solar radiation. This adds energy to the ocean surface. In winter, right, we see similar things, right, that we saw in the observations where there's these large, significant negative anomalies in the sensible and latent heat flux. And so this is a transfer of heat out of the ocean surface, and this is a transfer of moisture out of the ocean surface. It's important to note, though, that these are, because these are atmosphere-only simulations, this sort of added energy that's happening in the summer is not really felt by the ocean in these simulations. There would be an increase in energy input to the ocean surface, but that increase in energy input is not the reason why we see these negative fluxes of turbulent heat in the winter, right? These are only a response to a reduction in sea ice that is imposed within the model setup. And so, right, all we're seeing is that if you reduce sea ice here, you get increased heat and moisture out of the ocean. So if we had a coupled ocean atmosphere model or setup, we might see even larger increases in heat and moisture out of the ocean if the ocean was essentially able to feel this added solar energy that's being stored in summer. And so what does this mean in terms of the surface mass balance of the ice sheet? And so this is showing anomalies in precipitation minus evaporation and areas over the primarily over the ocean, that these large brown areas, these are showing where increases in evaporation exceed increases in precipitation. And so these are areas of net moisture addition to the atmosphere. And we can see these are most pronounced in these non-summer seasons and areas and over areas where there are reductions in sea ice. Right, and so if we think about how the atmosphere is circulating here on the eastward side of kind of climatological low pressure systems, and so one of the major circulation systems in the Antarctic is the Amundsen Sea Low. On the eastern flank of that, if this is circulating clockwise, we see that this increased moisture from the ocean is being advected toward the ice sheet, and it's falling as snow and contributing to positive surface mass balance anomalies on the eastern flank of these lows. And so one of these areas here is in West Antarctica. You can see this quite prominently in this winter season. It's also occurring in other seasons. Austral fall is another season where we're seeing kind of the effects of this enhanced moisture in the atmosphere being moved toward the ice sheet and falling as snow. And so if we think about the potential or overall, if we add these things up, it equates to about a 60 gigaton per year increase in snowfall over the ice sheet. And so to put this into context, this represents a large fraction of the recent mass loss from Antarctica that's lost through ice discharge to the ocean. And so it's about 45% of the recent mass loss via discharge in West Antarctica, or about 40% of the annual mass loss that's been observed with GRACE. And so if we kind of think about the potential consequences of this, right, particularly as it relates to projecting future changes in surface mass balance, those models that have too little sea ice, right, are likely simulating a warmer and wetter Antarctic and perhaps too much snow falling over the ice sheets. This then would potentially reduce Antarctic sea level contribution in modeling experiments that have too little sea ice. And so I started this presentation highlighting the major positive surface mass balance anomaly that occurred in 2022. And you're probably wondering, was that influenced by recent reductions in sea ice? And so, in other words, is sea ice to blame for what happened in that really anomalous year of 2022? And I think that's a great question, something that I've thought quite a bit about. And so again, right, this plot on the left is showing that more snow fell across Antarctica. It set record 4-decade-plus highs in surface mass balance. And if we look at what else was going on in Antarctica in 2022, sea ice was at or near record lows for much of the year, right? And so we're seeing very reduced sea ice and also very high surface mass balance. And so the analyses that I just presented would suggest that the ocean surface played a large role in this. And so what does the analysis show, though? And so we can start to get clues about what happened in that year by looking spatially. And over the course of the year, surface mass balance was 80 to 90% higher than normal in some areas. This is especially prominent here in this area of Wilkes Land, this sector of East Antarctica, where the 2022 SMB anomaly exceeded interannual variability. And so that's this kind of, again, the hatched area that you see here. There were hotspots in SMB over the Ronnie Filchner ice shelf in areas of West Antarctica, and especially in this sort of kind of eastern Drawning Maudland area. Yeah. And so given we're looking at 3 different products here, 2 reanalyses and a regional climate model, given that there's strong agreement in the magnitude and spatial character of these SMB anomalies, over the next few slides, I'll be just looking at anomalies in the ERA 5 reanalysis to try to explain what happened. And so how did all that extra precipitation end up in Antarctica? Well, we know that precipitation in Antarctica is known to be dominated by these sort of high magnitude or extreme precipitation events, or EPEs. Annually across the Antarctic ice sheet as a whole, EPE precipitation accounts for about 40% of the total annual precipitation. And so following Turner et al. 2019, what I've done here is classify EPEs in 2022 as when daily precipitation exceeds a 90th percentile climatological value of daily precipitation. So what we're looking at is like the top 10% of magnitude of daily snowfall events, and that's classified as an EPE. And so this plot here is showing that EPEs in 2022 accounted for a large proportion of the total precipitation. So this is showing like how much snow fell during EPE and what proportion of the total annual accumulation came from one of those EPEs. And these can explain more than 60% of the annual precipitation in places like the Weddell sector in 2022, in kind of eastern Drawning Maudland, here's a hot spot, and across areas of Wilkes Land and Adelie Land in East Antarctica. And so a lot of the snow that fell in 2022 was it was associated with one of these like high magnitude snowfall events, an EPE. And so this is looking now at the EPE anomalies in days. And so how many more or fewer days were there of EPEs? And anything outlined in the contour and hatched here exceeds interannual variability over a 30-year climatology. And what we can see with this is that there are broad swaths where there were 1 to 2 weeks greater EPEs in 2022 than normal. And so EPEs traditionally explain a lot of the surface mass balance anomaly, but they really had an outsized impact. There were more of these in 2022. And also notable is that areas where there were greater EPEs, and so that's these kind of red areas, these are also the same areas that EPEs made up a large part of that precipitation. And so, right, if we kind of flip back and forth, the areas where there are really these hot spots of how much those EPEs contributed, these are also areas where there were just a greater number of these events. On this plot, this also shows dots, and these represent where there were significant surface mass balance changes in that year in 2022, either positive or negative. And clearly, let's see here, there we go. Clearly, there was a strong spatial agreement between EPE and SMB anomalies. And so where there were more EPEs, these sort of red areas, these are where we have positive surface mass balance anomalies, and where there were fewer EPEs, for example, here in sort of western Drawning Maudland or in this Mary Bird Land area of West Antarctica, these are where there were actual negative surface mass balance anomalies. And so what drove those extreme precipitation events? Atmospheric rivers, ARs, these are long, narrow bands of enhanced water vapor transport. These are known to be an important component of Antarctica's surface mass balance because they really represent this connection between lower latitude moisture sources and as well as heat and Antarctica. And so what we've done here is assess atmospheric rivers using a polar specific AR detection method of Jonathan Willey. And we can see that like EPEs, ARs really had an outsized impact last year. There were more days with ARs and they dumped more precipitation. And so again, ARs are an important component of the surface mass balance. We know that a lot of the precipitation in Antarctica today results from ARs, but in 2022, they had an even larger impact than they normally do. And so on the left here in this plot, this is showing there are really large swaths of Antarctica. And so like West Antarctica, the Antarctic Peninsula, as well as Wilkes Land, these experienced significantly more AR precipitation in 2022 compared to normal. Why did this happen? On the Antarctic Peninsula, we know that, and West Antarctica, we know that when the southern annular mode is in its positive phases, this helps direct moisture transport and an increase in atmospheric rivers to the peninsula in West Antarctica. And in 2022, SAM, the southern annular mode, was at its second most, as an annual mean, at its like second most positive annual mean value ever observed. In this Wilkes Land region, we know that there was a kind of a semi-persistent blocking high that existed south of Tasmania and Australia and New Zealand that helped direct meridional moisture transport, namely via ARs, toward this sector of East Antarctica. On the right, this is showing that the greater snowfall delivered by these ARs also made up a larger relative contribution to the total snowfall. And so these delivered, right, again, they're delivering a lot of precipitation, but they're delivering 30% or more to some areas than they normally do. And so these were very impactful in 2022. Yeah, and so most of the surface mass balance anomalies that we see in 2022 can actually be explained by these EPEs or atmospheric rivers. But if you look at these plots enough, you can convince yourself that there are areas where the ARs and EPEs don't quite tell the full story. And so For example, there's this area near the Bellingshausen Sea, where there is generally more precipitation from atmospheric rivers. This is red. And you can see here that there's sort of pink here in this analysis, in this plot. But the AR impact does not stand out above interannual variability. And so this is partially the result of probably a persistent Amundsen sea low advecting both atmospheric river moisture toward this area, but also whatever other moisture is in this region toward the peninsula and kind of this Bellingshausen Sea sector of West Antarctica. So it's ARs plus something else. If we look at the longer term history of atmospheric rivers, we can see, and that's plotted here, this is showing the sort of the total precipitation delivered by them, and as well as their contribution, their like the fraction of the total precipitation delivered via an AR. We can see that they played a really central role in the surface mass balance of Antarctica in 2022. They delivered more precipitation than they ever have in the last 40 years. This was about 220 gigatons more snow than they typically do. So we're talking about a 50% increase or over 2 standard deviation increase more than normal. If we look at the spatial patterns of ARs, but also EPEs, we know that ARs were an important component of that moisture flux to Antarctica. Yet if we look at this blue line here, which is showing the fraction of the AR to total precipitation, this was not quite unprecedented. And so what this means, in other words, is that both ARs and non-AR precipitation was higher in 2022. And so that raises the question of what could this be? Right, and of course we can assess what was going on at the ocean surface, thinking about what potential role sea ice may have played. And we know that offshore West Antarctica, sea ice was low. It advanced later in the season and retreated earlier. And so there was more open water, especially in West Antarctica. These are also areas shown in blue here where there were significant increases in evaporation from the ocean surface. And so it's likely, especially with a kind of a strong Amundsen sea low here, that some of this additional moisture from evaporation was advected over the ice sheet and helped contribute to those positive anomalies in surface mass balance. Okay, so that was 2022. What about last year? If you are a follower of Antarctic sea ice, you know that 2022 was a big deal, and then 2023 was an even bigger deal. And so the Antarctic sea ice set new record lows in 2023. However, despite that record low sea ice, the Antarctic surface mass balance decreased. Now this plot shows the time series here of surface mass balance up to 2023. And so these last plots here are showing that there was a decrease in total surface mass balance relative to that extreme year in 2022. And so what is this? This is about 170 to 200 or so gigatons less snowfall in 2023 than occurred the year prior. And so 2023, last year, likely marked a return of the Antarctic ice sheet to contributing to sea level because there was less snowfall. However, surface mass balance was still relatively high. It was about a 1 standard deviation anomaly over climatology. And what we see is if we look at ice shelf surface mass balance, this was among the highest ever observed. And so this was the 3rd highest ice shelf surface mass balance in ERA 2 or the 5th highest in ERA 5. And so while ice shelf or floating ice SMB is not directly relevant to sea level, it is relevant to the health of the firn layer of ice shelves. The firn layer is really what dictates what surface melt does. Does it percolate in and refreeze if there's a lot of firn air content, or will it pond at the surface, forming lakes, which could impact ice shelf stability? And so increases in snowfall, especially over ice shelves, is relevant to the ice sheet's overall potential contribution to sea level. Interestingly, we're now looking at the MAR regional climate model here rather than RACMO for 2023. We see that ice shelf surface mass balance, and that's this lower plot here, this was lower in MAR, both in 2023 as well as overall. And so looking into this is at least partially the result of Mars simulating meltwater runoff from some ice shelves. And so this is sort of counter to what's generally conceived about melting in Antarctica at the surface today. Most of this water is thought to percolate into the firn layer and refreeze. However, Mars here is simulating some meltwater runoff. The issue is we don't really know whether this is correct or not. We don't have very good observations of what melt is doing today. And so we don't know what the fate of that meltwater is for many areas. And so this discrepancy, I think, is a nice plug, or really points to the need for improved observations and understanding of the drivers and magnitude and fate of meltwater. If we look at so 2023 wasn't quite, as a whole, not super anomalous like it was in 2022, but there were a couple months that really stood out. One of those is in March, and that's when there was a greater than 2 standard deviation anomaly in the surface mass balance. The other month here is November, where there was a slightly more reduced anomaly. That's shown here for the MERA2 and ERA5 reanalyses. It was a larger anomaly for ERA5 than MERA2, and so there is some discrepancy of what's going on between these reanalyses. Both of these months, both March and November, these were at or near record highs for surface mass balance for floating ice shelves. For example, in March, this for ice shelves specifically, this was either the first, second, or third highest surface mass balance ever recorded in these three methods that we are using to assess the surface mass balance. And so this is kind of interesting because if you look at these plots, right, March doesn't look all that anomalous, but if you look at November here, right, there's a really strong positive surface mass balance here in this kind of a western Dronning-Maud land area over the Wilkes sector. March, on the other hand, it's sort of like more widely distributed. So there's kind of different things going on in these different months. And so if we look at November 2023, that SMB, the story here is a lot like we saw in 2022 overall for Antarctica, where large positive anomalies in surface mass balance were associated with kind of these high magnitude precipitation events, or EPEs, and ARs, atmospheric rivers, were really the mechanism, and a positive anomaly in ARs were the mechanism that delivered this increased moisture to Antarctica. And indeed, for November, it was a series of ARs that contributed to really quite anomalous events over this sector, this Weddell sector of East Antarctica. This was, for this sector here, this was the largest ever recorded snowfall in November, and overall, I believe. And it also set other records like air temperature records. There's more analysis to come about this event for sure. But again, this is the story of basically ARs bringing moisture from far away to Antarctica. The more interesting story, maybe, the story that might relate more to what's going on in the ocean surface, is that big anomaly in March 2023. And again, this was where there wasn't really a very concentrated surface mass balance anomaly. It was more widely distributed. And so if we look at what was going on in that month, some of the surface mass balance anomalies, like this sector here, can indeed be attributed to positive anomalies in ARs. Across East Antarctica, this sort of Wilkes Land region as well, there are some positive SMB anomalies associated with that. However, there are also more broadly positive surface mass balance anomalies that are not related to atmospheric rivers in 2023. For example, this sector of the Ronnie-Filchner ice shelf and the associated Weddell sector of East Antarctica saw more precipitation, but this was not associated with, from what we can tell, an increase in atmospheric rivers. And so something else was going on here. This sector of East Antarctica as well, over kind of West Antarctica too, right? There aren't increases in atmospheric rivers that can clearly explain these increases in precipitation. And so if we look at it, what else was going on there, we can see that in most of these regions where there were positive anomalies in the surface mass balance, we see offshore negative anomalies in sea ice concentration. So this suggests some role of increased evaporation from the ocean surface, helping to contribute to more broadly positive surface mass balance in this month of March of 2023. And again, March of 2023 was kind of a big deal. It was more broadly, we saw more broadly increased snowfall over Antarctica. Okay, so with that, some takeaways. What we've shown through both reanalyses as well as the FM2 atmosphere-only experiments is that reduced sea ice can indeed drive important changes to the atmosphere, namely increased air temperatures and moisture content via evaporation from the ocean surface. This increased atmospheric moisture can lead to important surface mass balance gains over the Antarctic ice sheet that at least partially mitigate sea level rise. In 2022, atmospheric rivers were an especially important mechanism driving precipitation delivery over the Antarctic ice sheet. These contributed more snow than at any time over at least the last 4 decades, and this led to a record high surface mass balance for Antarctica and the ice sheet overall, subtracting from sea level in that year. However, if we look at 2022 and especially March 2023, those SMB anomalies are not all explained by atmospheric rivers or EPEs. And so what we see is that there are these offshore reductions in sea ice that spatially coincide with onshore positive surface mass balance anomalies. And so this suggests that reduced sea ice has indeed contributed to these recent positive surface mass balance anomalies. And then I think one of the biggest takeaways here is that we need to really get the ocean surface as correct as possible if we want to accurately represent snowfall over Antarctica. And so a couple like concluding thoughts related to that. There's been a recent, up until 2016, a lack of a sea ice decline prior to 2016. That lack of decline or relatively steady sea ice may have suppressed the surface mass balance of Antarctica, thus enhancing its recent contribution to sea level, right? So a lot less snowfall because there was more sea ice, allowing really the change in total mass balance of Antarctica to be increasingly negative, so adding to its sea level contributions recently. However, as sea ice has recently declined and it's going to decline into the future, enhanced snowfall via evaporation out of the ocean surface and falling advection of that moisture to the Antarctic ice sheet will at least partially mitigate sea level rise. But if models simulate too little sea ice, they may overestimate the surface mass balance, right? Too little sea ice means too much snowfall over the ice sheet potentially. If there's too much snowfall over the ice sheet, then our projections of sea level in the future may be on the lower end. And so overall, getting the ocean surface correct as possible is likely critical to getting the surface mass balance of the ice sheet and its total contributions overall to sea level also as correct as possible. And so I would just point out a few references. If you're interested in this work, we've published this a couple of papers last year in Journal of Climate and geophysical research letters. The 2022 SMB we discussed in the State of the Climate report, and then 2023's SMB anomaly is also going to be in the forthcoming State of the Climate report. I would like to thank those who have contributed to this research. Their names are listed here. Again, the NASA Cryospheric Sciences program for supporting this research, and thank you all for your attention, and I'd be happy to address any questions.
Thanks a lot, Luke. We do have some questions in the chat. There's one from Shanice that says, did you compare your Era 5 shortwave net to observational data? And curious about this because in a region of interest, Gulf of Mexico, I find that Era 5 is severely underestimated by almost half compared to GOES 16.
Yeah, that's a good question. Oh,
Letty had a follow-up that
okay.
is asking how Era 5 and Mera 2 compare for those variables.
In terms of shortwave radiation, I'm assuming. So to answer Shanice's question, we have not compared to other observational data sets. That's a really interesting point. We haven't assessed that though. Um, and also to Letty's question, how do Era 5 and Mera 2 compare for these variables? In terms of the energy fluxes, did not compare Era 5 and Mera 2. That's a good question. Overall, their surface mass balance is pretty similar, although they do show different trends over ice shelves, which is kind of interesting in terms of snowfall. And so they're overall pretty similar, but there are some important differences too.
I guess I was also curious if you had a sense of which one you would trust more than the other. I know certainly for temperature they look quite different, but I don't know which one I would favor.
Yeah, I'm not sure. I don't want to like promote one or the other right now. I am a little skeptical of Mera 2 in that it's coarser resolution. If we think about the snowfall and how important orographic precipitation is, like air masses moving onshore in Antarctica and rising vertically and condensing and dumping a lot of precipitation. Mera 2, coarser spatial resolution, probably doesn't capture those orographic effects as well as Era 5. But yeah.
Thanks. And then just one comment about the sea ice was, you mentioned about the low sea ice stemming from the difference in trends, but also if you just look at the mean state in the CMIP6 models, they really typically underestimate summer sea ice. And that's quite consistent across many models. And so I thought it was just worth kind of emphasizing that seems like that having it in that month especially would be an issue for SMB.
Yeah, that's interesting. Yeah, so I mean, my initial thought was that lack of summer sea ice might be the most important, but from what we've seen is that the other seasons, especially the fall and winter where there's reduced sea ice, this is where we can really like potentially make a bigger impact in terms of surface mass balance. And I think my thought about this is that really that Antarctic sea ice in summer is already really low. And so it may not, a further reduction in sea ice in summer may not be all that relevant to surface mass balance, but it's really those other seasons.
Yeah. Okay, I guess that's kind of good news in a way then.
Yeah, yeah, I guess so.
Thanks for the really nice talk.
Yeah, thanks, Letty.
And we also have, so Shanice replied that thanks for your response and presentation of your rich analysis. It might be important to check if Era 5 is representing shortwave accurately.
Okay.
And then Heiko says, do you have evidence for the link between sea ice mean state bias in global climate models and bias in precipitation over Antarctica? And do you have evidence for how that influences projection?
Yeah, Heiko, that's a really excellent question. Not something that I have specifically looked at, although Tom Bracegirdle and others in 2015, I think, kind of looked at the CMIP5 ensemble, and one of the things that they found was that models that have greater reductions in sea ice also have greater increases in air temperatures and precipitation over Antarctica. And so there's kind of this link between how much sea ice is reduced in the future and how much snow and the temperatures over Antarctica as well. So that might kind of answer that question.
Okay, are there any other questions? Well, I guess if not, we can stop there. So thanks again, Luke. Thanks for coming.
All right. Thank you, Patrick. Thanks, everyone. Happy equinox.
Yes.